Right. So good morning, everyone. I'm very happy to be here, and I'm pretty new for the P4 and P4C community. So, and as usual, it's great to see the faces behind the names. Uh, so while I'm kind of new to P4 and all these things, but somewhat about myself. So I spent quite some time and still doing lots of work within LLVM, like with few contributions dated back to like almost 20 years ago. So I own few, still couple of components in LLVM. I also did some contributions to GCC and its derivatives. So if you kind of remember what was LLVM GCC 4.2, then you could blame me for that. I also spent some time on the differential Swift, so it's autodiff, like automatic differentiation in the Swift language. Plus, well, I'm doing a few things in like, other open source projects, and some of them are not even compiler related at all. So given that, and as I said, I'm pretty new to P4, and sometimes I might be like producing some rants about some, design things and so on, but it's just mostly because I'm a little bit biased to see what is other way and so on. All right, and today, as Aldi mentioned, so we are going to talk about the performance of P4C, the P4 reference compiler. Well, usually the reference implementations are not like intended to be fast. They are, well, their main purpose is to be correct per the specification. But the problem here is that there is no other production-ready P4 compiler around. So certainly there are some other like academia produced like front end. So well, but they're not, unfortunately, well ready for the like entire production use. And meaning that the downstream users who want to like deploy P4 in their products need to rely on P4C. So that means that we have the kind of dilemma. So we either need to improve P4C or develop something else that could be used instead. But given the whole like 10 years of like knowledge and development accumulated in the, well, P4C, well, at least doesn't seem to be the viable option today. Well, maybe it will eventually, and well, but still it kind of lost effort. So let's see if we can try to, well, see if we can improve the P4C itself. All right, so here is our baseline. So for our baseline, I took the P4C release that was released back in January. Well, this is not the actual test case that we started to work on, because the actual problem was like downstream. But my intention is to show that like all the kind of issues I'm going to discuss and all the approaches well, could be well readily reproduced with the mainline P4C flow. So let's take this particular test case we have in the code base. So it's just like 10K, like less than that, of straight P4 14 code. And if we just run this test case, so we can see that the compilation time of that, well, on my laptop that sits right there, is like 15 minutes, or 50 seconds, sorry. Still, if you come from like C, C++, any other language background, you might feel that probably the compile time for just 10K lines of code is in 50 seconds. It's quite a lot. So it's not, before it's relatively simple language. So we're not doing any like crazy template meta programming. We're not checking all kind of like protocol conformances and all of the craziness, right? So, but still, like 15 seconds for 10K lines of code, it's a lot. But let's do some deep dive and see what's going on there. If we just fire up the profiler, then, okay, we'll see that the front end takes like 80% of entire compilation time. So, okay, let's see what's doing that. If we try to do the profile with inverted stack, we can readily see that 40% of time, well, it was back in January this year, was consumed by the like RTTI boilerplate. So meaning that we spent like 40% of the whole compilation time just to, well, doing all that RTTI calls. Where all these RTTI calls came from. So they are all from the downcasting and identity checks. So this is kind of like unroll example. So these days they are mostly hidden behind it, like that iCastable interface, if you're familiar with the P4C internals. So, but still, so certainly, well, because the compiler operates on the like iron nodes, so it has to do lots of like type checking and like upcasting, downcasting, and do all the kind of like type checks and so on. Slow RTTI is not a new problem actually. So the generic like C++ runtime type information like queries are quite slow, and the reasons for this is kind of historical. If we talk from the C++ background, so in essentially the like, I won't deep dive into the like lots of details why it is so, but well, the standard committee did not want to be very intrusive, so they kind of designed the RTTI as a supplementary thing with the like hope that it was not be the thing that is well, used like on every second line of code. But certainly there are some implementations and some code base that, well, execute RTTI a lot. And another reason why generic RTTI is slow, because it has to deal with like arbitrary open class hierarchies. And well, yeah. And it's pretty hard for compile itself to inline or optimize through these calls because, well, it's just runtime library calls with some supplemented with compiler generated metadata. And to solve this problem, many projects implemented their own like plugin RTTI implementation for closed or semi-closed class hierarchies. There are lots of examples right here, so I just collected a few of them. So certainly it's, well, it's like very in my head of like doing stuff in LLVM. So LLVM clan has their own like RTTI implementations under the hood, and MLR as well, certainly. Like if you remember what Microsoft Foundation classes are, there is some RTTI like handwritten RTTI under the hood. I would say every game engine has its own RTTI implementation, like Unreal Engine, like Lumberyard, like whatever. Because, well, they all operate on the objects. They do want to do this like fast downcast type checks and so on. So, and well, as usual, for me, the first idea, okay, we have pretty well documented, pretty well separated RTTI implementation in LLVM. Can we just, well, reuse it from LLVM for P4C iron nodes? And sadly, no, because, well, the overall P4C RTTI, oh, sorry, P4C IR design for the node hierarchy is quite, well, I would say more Java style with multiple inheritance, with like abstract and visual base classes. So meaning that we cannot use just the static cast for downcast. We actually need to know, for downcasting, we need to know the offset of the base class in the derived class. And well, if we add like lots of stuff on top of that, well, with like multiple virtual inheritance, so it's, well, quickly might become the mess, and meaning that, well, we cannot even do the things by hand, and we need to have the compiler to do the majority of work for us. So, and we did the like new RTTI implementation, well, designed specifically for the P4C needs. So, and there are like two components there. First of all, because the code for the IR nodes, they are generated during the compile time. So by that, like IR like, generate a binary from the definition files. So we can actually auto-generate a bunch of the things and, well, like type IDs and whatever. But beyond that, we also added a few things. So it could support other arbitrary semi-open-ended class hierarchies. So you just, well, derive from the single base class like RTTI base that does all necessary like heavy lifting and actual implementation. So we utilize the compiler to generate the well, those, well, the so-called like these adjustment functions for us, so that like, so compiler essentially forces to calculate the offset of the base class in the derived for us, even if we have like multiple inheritance stuff. So the implementation is also compatible with the downstream code. So if it still uses the like plain C+ RTTI, so everything is like compatible at all. The overhead of this implementation is quite low. So just, well, one additional virtual function call plus some easily optimizable like lookup code, and that's it. Let's see what was the effect of that new architecture implementation. So straight from that, we get like more than 40% reduction of the compile time. So we went from 16 seconds down to like 9 seconds. That's great. And yeah, if we look into the stack trace, like in the profile with inverted stack, so you see like no traces of FTI runtime calls at all. So you could, no, not even here. Okay, so this was the first thing, but let's check if we can proceed even further. If you look into this particular case, you see that there are lots of the, like in the top trace, there are lots of cases with the like, well, essentially the memory allocation and some code that's used by the visitors. So visitor is the, I would say, central class within the whole P4C compiler. It's called on, like, if you want to do anything with the like IR, you essentially invoke visitor, and that's it. And each visitor maintains its internal state in the hash table. So usually it's just the map from node itself to some internal state. For inspectors, it's just a couple of Boolean values. For modifier transform, it's a little bit more complex thing, but still. And if we just count how many times the visitor is invoked on this particular case, you could see that it's indeed the central class here, because we have like more than 120K invocations of inspectors. So, and like 86K invocations of transforms. So totally, it's like 200,000 invocations of visitors just for this test case. And it's not even large things. I saw like cases when we have like 10 times more. So, and under the hood, this hash table is just backed by the ordinary unordered map. So it's not the fastest and not the best implementation out here, well, due to many different reasons. There is huge malware traffic to create and destroy these hash tables, because essentially every visitor invocation just creates the like new hash table from scratch. So it allocates all the necessary things. I would return to this statement lots of times, but the because the P4C uses garbage collector, the memory allocation is terribly expensive, because it has to like zero all allocated in free memory. The GC itself is pretty slow compared to other memory allocators. If you can afford to turn off the GC for your project, then you can like easily have like maybe 25 and even like 50% of speed up for free. All right. However, we cannot simply, well, replace the things with some other implementations, because, well, pointer to my values do escape, so we cannot like drop, like use some other implementations. Plus, it turned out that the close inspection, that few places rely on iterative stability during insertion. This is certainly not at all. So there are kind of like unnecessary lookups and so on. And what we noticed that in many cases, these maps tend to be pretty small. This is usually true for the nested visitors. Then you could invoke like somewhere like in the end. So, but sometimes these maps could be quite large if you just like run visitor on your whole program. All right. Fortunately, we had the great map implementation out there. And we, because of the dependency on the upsell library that we had to consume due to protobuf update, so we can, so there was kind of synergy. So we just dropped in the much better library. We did some, well, we rewritten the code not to do some unnecessary double lookups. Plus, we also do some kind of like pre-allocation of 16 map slots by default, meaning that for small case, we just do the single memory allocation in the end, and that's it. All right. So the outcome for this was also quite viewable. So we have like 25 reduction of the compile time here. All right. So now we from 16 seconds we are down to 7, and let's see if we can improve more. Further analysis revealed it's not very visible here on this particular test case, but for other test cases, we saw that the majority, like not the majority, but lots of time is spent on the various lookups into two central maps inside the compiler. This is a reference map and type map. So, and as you might know, the IR modifications is quite expensive because both reference map and type maps, they have to recalculate it from scratch after every IR modification. Let's ignore this for the moment. So we will return to this, well, not very great idea later. But let's see what is inside this map. And inside this map, I would say this is yet another data structure that is terribly misused around the whole P4C code base. And this data structure called ordered map. So it's routinely used as the P4C map everywhere. And usually, if you want to use it, it's like 95% cases that it's a terrible idea. Why? It's very, very expensive. So it's essentially ordinary map plus list. It has huge overhead. So you have at least 8 pointers per single entry overhead here. So it does lots of the memory allocations. It has slow lookup time. Well, plus, as it turned out, that there is no iteration at all in these maps. So meaning that, well, we don't need ordinary map at all. Come on. All right. So, and let me return to the garbage collector. So I understand that, well, due to historical reason, P4C is backed by the garbage collector. But the garbage collector in C++ is overly conservative. It has to scan the whole allocated memory. And there's a huge difference as compared to the garbage collectors we are having in other management languages like Java or C# or Golang, because in these languages, usually garbage collector is much more precise because it uses the compiler-generated metadata to know where the pointers are. So we don't have this luxury like in C++. So it has to scan the whole memory. So plus, that means that there is the overhead as it has to zero out the whole memory on the allocations and deallocations because, well, it only, well, can detect the pointer by the values. As I already said, so it has non-negligible overhead. Plus, it's pretty unpredictable because we saw lots of memory usage spikes. So, and you can change your code pretty slightly and has like 20, 30% execution time differences. I saw the cases then erratic GCB, like garbage collector behavior, well, just doubled or tripled the whole compilation time. Plus, the use of garbage collector kind of encourages the poor coding practices. So we tend to leak a lot in the P4C inside. Instead, even in the simple cases when we know the lifetime of everything inside. So plus the whole structure of the compiler kind of, well, it's garbage collector hostile because what we have is we have the pass manager that executes the passes. The passes itself are like have the nested pass managers, etc., etc., etc. And as it turns out that the top level, like front end or mid end or back end pass manager, actually owns everything, meaning that almost everything is uncollectible for the garbage collector. Because if your pass has the internal state, and if you're not explicitly release, and it's not enough just to call the clear on your map, because it does not, it's only reduce the capacity, it does not freeze the memory. So the garbage collector won't collect it. So meaning that if you trace the memory consumption of your, of the entire compilation time, you see it grows almost, it grows until the end of front end, then it drops because the front end pass manager, well, just dies. Then again, it grows through the mid end and it dies and so on. So, well, we saw lots of cases of just, well, the ordinary compilation of the program consumed like 16 gigabytes of RAM, so it's terrible. All right, so let's see if we can improve a few things here and there. So there's the results of the, well, when we improve the maps internals plus some usedef malloc traffic, and we obtained another 40% reduction. As I said, so both reference and type maps are recalculated from scratch after every IO modification. Well, that's probably not the best idea out here. So even more, it's often recalculated before every pass execution. So you have the typical combo of like resolve reference plus type checking plus pass. Even more, in some cases, it's recalculated multiple times during pass execution. The inliner used to recalculate the reference map after inlining of every single function. So I had the example when a reference map, like reference resolution, consumed like 300 milliseconds, but the inliner had to inline like 80 functions. So meaning that, well, we have like 25 seconds spent only for resolve references only in the inliner. That's kind of not the greatest idea out here. All right. So fortunately, like maybe a couple of years ago, Chris like developed that resolution context pass mixing. So it's much more local and fine-grained reference resolution. So, and unfortunately, he did not have the time to convert the whole code base on that. So, well, and what we did is that we essentially ported almost the whole front end to the resolution context. Well, this is not the correct statement. So, like yesterday, I landed the pull request that converted maybe 80% of mid-end. So, and there is another pending pass that like pull request that, well, with further modifications. So backends are on your own, sorry. Plus there were other like changes and improvements in the internals, like C-string caches, some type checking, type inference improvements, plus you've def memory consumption. And this is what we having. So the first thing is what we have originally. So and in the end, we ended with like 3.5x improvement in the compile time. The check before is also improved. So it's not apple-to-apple comparison because there are different number of tests, but still. And here is one of the example of the large downstream application. So it's 5 times larger than that test case I was talking about. And the compilation time before was like more than seven minutes. So that's terrible compile time, meaning that your iteration time for the development is, well, really struggling. These days is like less than 1 minute. So it's like 7x improvement, but still quite a lot. Sorry. Pretty slow. P4C is terribly slow compared to other compiles we're having out here. And definitely more speed up is desired. I would probably say that, this is my last slide. So I would probably say that the one of the reasons is that immutable IR impose lots of overheads. Like 90% of time, the compiler just allocates the memory and clones and allocates the memory and doesn't do anything else. So we need to work on reduce the memory allocations and overheads as much as possible. Like few other like ideas is, well, maybe switch to reference counting, try to allocate lots of things in line using so-called like training objects like idiom. Well, iron nodes currently, they're just like running through the like heap and the sort, but why we don't allocate them from some pool or arena? We also need to reduce the visitor overhead or maybe switch to entirely new IR, like MLR, for example. Well, so there are lots of ideas here. All of these changes are quite invasive. So, well, this certainly might affect downstream projects. And I think that's it for me. So thank you.
Your question? We'll go one quick one.
Okay.
Thank you. Yeah, someone that uses the compiler, the open source version excessively, I really appreciate all the changes because I also noticed a good speed up on my tools and everything, especially interpreters. So I have a question on, so a lot of these changes, they're somewhat band-aid fixes for a structural problem the compiler has, which is, I think, garbage collection and, well, the way the visitor framework is constructed. Do you think it's worthwhile to look at these particular two issues and try to come up with something new that could fix it, either getting rid of garbage collection or trying to come up with an LLVM style kind of system? Even though it may be a breaking change, it could be very beneficial.
Yeah, so I really think that, well, I'm not quite sure about the like redoing the like visitor concept because, well, lots of the code that just relies on that, and so and it will be just, well, explosive changes. So we just like explode everything. But I definitely think that we need to work on better ownership in the IR. So it means that tool allocation, properly reference counting, some kind of like IR context that would own the nodes and would like allow us to, well, do the things here, well, will help greatly. So, well, because currently they're just like some objects allocated from like nowhere and so on. So yeah, things like that. This still would be pretty invasive change, but at least it would be much more localized. And well, I even had a couple of ideas that we might even like develop some like tooling on top of like Clang tidy, Clang modernized that would allow us to do some kind of like auto upgrade of the code. So instead of rewriting the things by hand.
Thanks.
Oh, thank you.
Quick one out.
So first of all, thanks again for doing this excellent work. Just wanted to know, can there be a situation where the backend may end up undoing some of your excellent work? As part of this work, can we expect some guardrails or policies, rules for developing the backend, or do you think that is not?
Yeah, right. So actually, it's also kind of right. So we saw lots of cases when the well, backends tend to like be in some cases even worse, like trying to use like C strings everywhere, even for like temporary interim strings, or trying to, well, do the things in, well, or even like copy the code from other places that was not well structured. So yeah, definitely the backend should probably see the movement, what's going on in the front end and the mid end, and try to adapt some of these ideas and some of these practices. There are lots of different backends, even in tree, and there are some other backends out of tree. So, well, we cannot just convert all of them. So it's up to backend developers to try to adapt to this practice. For example, getting rid of reference map and type map, and try to think about the use of their data structures and the like memory allocation patterns and all these kind of things.
Thanks.